Quantum computing represents a fundamentally new approach to computation, one that could revolutionize how we process information. Classical computers process information using bits. A bit can be in one of two states, 0 or 1, but never both at the same time. Quantum computers, however, use quantum bits or qubits. Unlike classical bits, qubits can exist in a state called superposition, representing 0, 1, or both simultaneously. This superposition property enables quantum computers to encode exponentially more data and perform many calculations at once. As we add more qubits, the computational power scales exponentially. With just 50 qubits, a quantum computer could potentially perform operations that would be impossible for today's classical supercomputers. Now that we understand the fundamental power of quantum computing, we can explore the key quantum properties that make it possible. Classical computers use bits, which can only be in one state, either 0 or 1 at any given time. Quantum computers use qubits, which can exist in superposition, meaning they can be 0, 1, or both simultaneously. In superposition, a qubit exists as a combination of states. Mathematically, we represent a qubit as alpha times 0 plus beta times 1, where alpha and beta are complex probability amplitudes. When we measure a qubit, its superposition collapses to either 0 or 1, with probabilities determined by alpha and beta. One of the most powerful aspects of quantum computing is the exponential scaling of qubits. Each additional qubit doubles the computational space. A single qubit can represent two states simultaneously. 2 qubits can represent 4 states. 3 qubits represent 8 states. And n qubits can represent 2 to the power of n states. Entanglement is another powerful quantum phenomenon, where qubits become correlated in such a way that the state of one instantly influences the other, regardless of the distance between them. When we measure one entangled qubit, we instantly know the state of the other. If we measure qubit A as 0, qubit B must be 1, and vice versa. Entanglement enables applications like secure quantum communication, quantum teleportation, and enhanced quantum algorithms, making it a crucial resource for quantum computing. Quantum computers harness the properties of quantum mechanics to achieve computational scaling that classical computers cannot match. Classical computers scale linearly with the number of transistors, shown in teal. If you double the components, you roughly double the power. In stark contrast, quantum computers scale exponentially with the number of qubits, shown in purple. The number of possible computations is 2 raised to the power of n, where n is the number of qubits. This exponential scaling allows quantum computers to tackle problems that are intractable for classical computers. Quantum computers excel at complex simulations, like modeling quantum systems and molecular interactions, which would take classical computers centuries to compute. They can solve optimization problems in logistics, finance, and manufacturing by exploring vast solution spaces simultaneously. In cryptography, quantum computers can break many current encryption methods while also enabling new quantum-secure protocols. Finally, quantum search algorithms can find items in unsorted databases quadratically faster than classical methods, with profound implications for data science. This exponential computational advantage is what makes quantum computing so revolutionary, enabling us to solve problems previously thought impossible. Recent years have seen significant progress in quantum computing capabilities. In 2019, Google's Sycamore processor demonstrated quantum supremacy, completing a task in minutes that would take classical supercomputers thousands of years. IBM reached 127 qubits with their Eagle processor in 2021, followed by the 433-qubit Osprey in 2022. By 2023, IBM unveiled their Condor processor, breaking the 1,000-qubit barrier. This progress has led to practical applications across several domains. Quantum annealing techniques developed by companies like D-Wave are solving complex optimization problems from logistics to traffic flow. Even as we wait for full-scale quantum computers, quantum-inspired algorithms run on classical systems provide performance boosts for many business problems. Organizations are already planning for quantum-safe security, to protect against future quantum threats to current encryption methods. Cloud-based quantum services are now making quantum computing accessible to enterprises without requiring specialized hardware. IBM Quantum offers access to over 20 different quantum processors, with both public and premium access tiers and a visual quantum composer interface. AWS Breakit provides a unified development environment to build quantum algorithms, with access to multiple quantum hardware providers and a pay-as-you-go pricing model. These cloud platforms facilitate integration of quantum algorithms into existing enterprise workflows. Organizations can now define problems classically, process them on quantum hardware, and integrate results back into their business systems. This hybrid approach enables businesses to start exploring quantum advantages while the technology continues to mature. Industry adoption of quantum computing will unfold over the coming decades, with different sectors adopting at different rates. Finance and pharmaceutical industries are positioned to be early adopters, likely within the next 3 to 5 years. Financial institutions will use quantum algorithms for portfolio optimization, risk modeling, and detecting sophisticated fraud patterns. The pharmaceutical industry will leverage quantum computing for accelerating drug discovery, analyzing complex protein folding, and genomic sequencing. In the medium term, within 5 to 10 years, aerospace and energy sectors will begin leveraging quantum computing capabilities. The aerospace industry will optimize fuel efficiency, flight routes, and design advanced materials with more favorable properties. The energy sector will benefit from quantum simulations for nuclear fusion research, power grid optimization, and more efficient carbon capture technologies. By 2030, quantum-enhanced hybrid computing is expected to become the standard approach where classical and quantum systems work together. This hybrid approach leverages the strengths of both systems. Classical computers handle pre-processing and post-processing, while quantum processors accelerate specific complex tasks. This hybrid model provides a more practical approach for the near term, allowing organizations to begin leveraging quantum advantages without waiting for fully fault-tolerant quantum computers. Market projections show significant growth for quantum computing. According to McKinsey, the quantum computing market is expected to expand from about $5 billion in 2025 to approximately $80 billion by 2035 to 2040. Quantum computers pose a significant threat to our current encryption methods. Modern encryption relies on mathematical problems that are difficult for classical computers to solve. However, quantum computers can solve these problems exponentially faster, effectively breaking current encryption standards like RSA and ECC. This has led to the development of post-quantum cryptography, which can resist attacks from both classical and quantum computers. Various approaches include lattice-based cryptography, hash-based signatures, multivariate cryptography, and isogeny-based cryptography. The quantum computing market is poised for significant growth in the coming decades. Experts project the market could grow to approximately $80 billion by 2035 to 2040, driven by advancements in quantum hardware and increasing industry adoption. When it comes to ethical considerations, the majority of quantum computing experts remain optimistic. A recent survey found that nearly 75% of experts are more excited about the potential benefits of quantum computing than concerned about its potential for harmful purposes. However, there are significant concerns about equitable access to quantum computing resources. Nearly 65% of experts worry that securing quantum computer time will be difficult for many organizations once the value of quantum computing is proven. Addressing these concerns requires developing cloud-based quantum services, promoting international collaboration, and creating educational resources to ensure broader access to quantum technologies. As quantum computing advances, balancing security needs, ethical considerations, and equitable access will be crucial for realizing its full potential.